Okay, so let's move on from just carbon and hydrogen to include oxygen now. So we've talked about alkanes, alkenes, alkynes, cycloalkanes, and we have touched on those groups having a halogen as well. But once we add an oxygen, now we get a lot more functionality, a lot more chemistry it can do, and it gets a lot more interesting. So as I'm progressing through these lectures, the importance of the group is increasing. So if I have just hydrogens, carbons, then it's kind of boring and I can name it. But if I add oxygen now, it's more important because it can do more chemistry. So now my longest chain has to have that group attached to it. It has to have that O attached to it. So when I have oxygen in my hydrocarbon, I can have an alcohol, an ether, an aldehyde, or a ketone. So alcohols have a carbon with an OH group attached. And as you can see in this example I have down here, I went back and got that isopropyl alcohol and I put it here so that we can see what it looks like. It can be anywhere on the chain, beginning, end, middle, but whatever carbon that group is on, the chain has to be numbered from the end closest to that group because it's the highest priority. It does the most interesting things. And so even if there's a longer chain somewhere else, if you have to have that OH somewhere else, you can't name it that way. You've got to name it with that carbon with the OH on it in the longest chain. And we would number from the end closest to that OH group. And it doesn't matter in this case which way we go because we'll get the same name. And the alcohol ending for the alkane, we change the final E to an OL. And so instead of saying isopropyl alcohol, which is a common name, what a chemist would call it is 2-propanol. And you'll notice there's a dash between numbers and letters. If I had more than one number, I put commas between them and then dashes between numbers and letters. So here are some more examples. I've included the common name as well as the IUPAC name. And so this top compound here on the left has 4 carbons, but I can't name it with 4 carbons. And so I can choose any carbon at the end to be carbon 1, go through the center carbon, and then go to any other carbon. And I could only get 3 carbons. So I could name it 1, 2, 3. I could name it 1, 2, I could name it 1, 2, 3, as long as I include this central carbon. And that central carbon is carbon 2. So this is going to be a propanol. And it's going to be 2-propanol because it's on the second one. And then if I highlighted this part of it as my longest chain in my alcohol, then we would see I just had this one methyl group still to name. It's on the second carbon, so it'd be 2-methyl 2-propanol. Here we have a ring. And in this ring, there are 6 carbons. This one has to be carbon 1, so I don't have to put a number. If you put 1 cyclohexanol, you can. But we need cyclo to tell me that it's in a ring. We need hex to tell me there's 6 carbons in that ring. And then the OL tells us that there's 1 OH group on there. Here, my longest chain is going to start right here with this carbon, 1, 2, 3. And so it's a 3-carbon long, but it has a double bond. We have to name this carbon number 1 because it's the highest priority group. So this is 1, 2, and 3. Double bonds between 2 and 3. So it's 2-prop, and we change the AN to EN. So 2-propene, 1-all. The 1 tells me the OH is on the N carbon. The 2 tells me this double bond is between carbons 2 and 3. And common names start to really not make any sense. Here, my longest chain is 1, 2, 3, and you could go up for 4 or down for 4. So this is going to be a butanol, and this has to be carbon 1. And I do need this one because this OH could be on this one or this one. And then the 3rd carbon will have our methyl, And then there's our fourth. So 3-methyl, 1-butanol. If I want to make an alcohol, the easiest way is to take a alkene, and in the presence of some acid and water, I can create an alcohol. This reaction is a symmetric alcohol, and I'm not going to get into a lot of details about how this mechanism works. If we were in class, we would have gotten to this earlier, and I would have gone through mechanisms because they're kind of fun. So that's alcohols. Ethers are the second one I'm going to talk about today, and then I'll talk about aldehyde and ketones tomorrow. So ethers are the first known anesthetics. They contain a carbon, oxygen, carbon in the longest chain. When you do this, you're going to look at the groups on each side of that oxygen, and you'll name each of those carbon groups, changing the final ANE to YL, indicating it's a substituent on that oxygen, and you add the word ether. So in the example down below, this side has a methyl group, this side has an ethyl group. Ethyl is alphabetically first, so I say methyl, ethyl, ether. So ethyl, methyl, ether. Pretty straightforward. When I want to make an ether, I typically take one alcohol, put it in a solution with water, with sulfuric acid and water, just because we need a certain amount of solvent. We don't want the alcohols to get too concentrated, or we can get all sorts of crazy things happening. This is sometimes called a dehydration reaction because we are removing a water molecule between the two alcohols, and we always end up with a symmetric or the same two groups on our O8, our oxygen, our ether. And so when we have two groups that are the same, we can use one of our prefixes saying di-ethyl. I have two ethyl groups on an oxygen in the longest chain, so diethyl ether. In this case, sulfuric acid is a catalyst. It is not a reactant. It is regenerated at the end of the reaction. We generally heat it up a little bit. Okay, so I'm going to stop here today, guys. You will have another lecture video tomorrow. And Thursday we will meet in teams as a final goodbye. You've been a great class, and you've really worked hard. I appreciate all your efforts, and I know this has been hard on all of us. So thanks, and I'll see you tomorrow.